I am LV and I will talk about part 1 of lab 3. Based on the schematic diagram, we have converted it into the functions of the input of JA, KA, JB, KB, and DC. And from datasheet, we found that the reset and set input must be set to high so that it does not affect the operation of flip-flop. Then, we also refer to datasheet to fill in the table and then determine the next state output. Finally, we came up with the state diagram. To test the transient state, which is 111 and 011, we can use 010 and set KB to 0, because the next state of 010 will be 101. By setting KB to 0, we will get the output of B equal to 1. Also, to turn 110 to 011, we also set KB to 0 because the next state is 001. And to keep B as 1, we set KB to 0. Then the output will be 011 based on the table. Then we are going to test the result. So, firstly, the output will be 00, then the next step will be 010, 101, 100, 110, 001, and back to 000. Then at 010, we test the output by setting KB to 0. Then we get 111 and setting KB as 1 again. We test the result. 111 will go to 100, 010, 101, 110, and 110. We can set KB equal to 0, then it will become 011 and set KB equal to 1 again. It will back to 100, 110, 001, and 000. That's it.
I am Janice and I will be doing part 2, B and C. The reason why we only choose B and C and not A is because we found out that one of our LED at the LED module is not functioning. So therefore we decided to do part B and C instead. Part 2b, we constructed the circuit based on the given function of min terms using an 8-to-1 multiplexer and a single gate. So based on the given function, we tabulated the truth table here. And based on the truth table, we constructed the schematic circuit diagram using 74HC151, which is the 8-to-1 multiplexer, and a single NAND gate. So to prove based on the truth table, when A, B, C, D is low, F is low, and when D is high, F is low. When C is high, F is low. When C and D is high, F is high. When B is high, F is high. When B and D is high, F is high. When B and C is high, F is high. When B, C, and D is high, F is low. When A is high, F is high. When A and D is high, F is low. When A and C is high, F is high. When A, C, and D is high, F is high. When A and B is high, F is low, and when A, B, and D is high, F is high. When A, B, and C is high, F is high. When all of them A, B, C, and D is high, F is low. That's all. For part 2C, we are required to implement for the function of maxterm using 1 to 8 decoder and a single gate. For this circuit, I will be using the 138, which is the 3 to 8 decoder and a 3 input NAND gate. So this is how the circuit diagrams looks like after deriving from the truth table. So when ABC is low, F is low. So when C is high, only C is high, F is low. So when B is high, F is high. So when B and C is high, F is low. When A is high, only A is high, F is high. So when A and C is high, F is high. So when A and B is high, F is low. When all three of them are high, F is low.
I am Lonnie Chung and I'm going to explain about Lab 3, Part 3. So from here, we turn the function into Carnot map. And from this Carnot map, we can see that we estimate that the hazard will happen when the B value change from 1 to 0. So we estimate the output should be stay at 1 for the whole time, but it goes to 0 and back to 1. And this is where the hazards happens. And this type of hazards, we call it as static 1 hazards. Okay, go to the circuit here. After we design this circuit, we can see that the hazard happens when the value of B change from 1 to 0. You see the hazard happens when the value of B change from 1 to 0. And that's it. So to remove the hazards, we add in one more NAND gate, and the input is A and C, and we connect this one to 3 input NAND gate, and the other 2 input, which is from previous one, which is A, B not and C, B not, to resolve the hazards. And from this construction, we can see that the hazard is clearly being removed and the output stay at 1.